All right, do that. All right, so where were we? So what we were doing last week is we got to the idea. So I was looking at, so the sort of part one, what I was doing is I was looking at intuitionistic propositional logic from what I'll call a provability perspective. And this is what I mean by that is the following. This is kind of like a traditional logic point of view where we had the basic judgment being A true, meaning that A has a proof, so it is provable, okay? And we could define, if we wanted, it'll turn out to be definable, but we could think of this as A false as meaning A has a refutation, which is really just a kind of proof. This is really the same as saying the negation of A we got to would be true. But sometimes it'll be useful to sort of think of it like that. And we were trying to develop some ideas, connect this up with traditional treatments of logic by speaking in terms of which things are provable. So we had these things as this was our primitive atomic judgment, and then we had the notion of a hypothetical judgment. Like where we have a bunch of hypotheses and we have logical entailment following from that. And then what we did, just to remind you, is we said if you look at the intuitionistic propositional logic, that is, we have the connectives in conjunction, implication, truth, disjunction, and falsehood, we got the structure of what was called the Heyting algebra. And I mentioned this in a follow-up, which is, to put it briefly, is it's a lattice, which means it's a preorder with all finite meets and joins. A lot of times in computer science, people throw the word lattice around like they get to let it mean whatever they want it to mean. But it has a very definite meaning, which is we should stick with, which is preorder or partial order typically. There's that whole issue. So it's a partial order with all finite meets and joins. Okay, meaning greatest lower bounds and least upper bounds, and it has exponentials. Okay, which are given by implication. So b to the a is given by the implication A implies B. And then I asked you to do as an exercise that every Heyting algebra is distributive. Okay, so you can do that. And then we enriched that further, and we noticed within here we defined a negation, which I've already used here, but just to remind you where we are, we defined the negation of A. We just defined that to be A implies false, which could also be written as false to the A, if you use the exponential sort of notation that is often used when working with like these order structures. We define that. And this was we defined this as essentially the largest C that is inconsistent with A. And we gave the rules for that. And that really just follows from the fact that the exponential has a similar universal property, and I'm just specializing it to the negation. So we did that. So we're going to play around with this. That's why I want to revise this. So we got to the notion of a Heyting algebra. And then I mentioned on the piazza that you can say that in IPL, so using this notation, as I mentioned, this is sort of invariably written gamma. I can prove that, well, gamma gives me a true if and only if, in a suitable sense, I'll just write star for lack of imagination. This is less than A star in every Heyting algebra. Okay, so this is a soundness and completeness result. The star just means, and really I should give some other notation here. So what I really mean is you take the interpretation of the proposition each of the propositions into the High-Ting algebra and conjoin them on the left, and then that gives you, that's what I mean by this. So this is a slight abuse of whatever that meant. This is a slight abuse of notation there. And we're going to rely on this in a minute. I'm just going to mention this in a moment. So I asked you to look at that, and I outlined a proof of this on the piazza, and I'll give you that as an exercise as well. And the key thing was the idea of what is called the Lindenbaum algebra. And if you've studied any logic, you've run across the idea of the Lindenbaum algebra. So the key to the proof is constructing what's called the Lindenbaum algebra. Okay, and then we had the idea of a Boolean algebra. And the point I'm making is, by contrast, is that not every High-Ting algebra is a Boolean algebra. That's what's important. Every Boolean algebra is a High-Ting algebra, so it's a lattice, okay, as the same. And it is complemented, and it is distributed. Okay, and so what do I mean by complemented? That is that A bar is the smallest C that, fills up A, or so we can say such that if I take A and join it with C, then that will be at least top. But of course, it's at most top, but we can write it like that. So it has a kind of universal condition as well. All right, so that's the sort of usual setup. And then you can, in the setting of a Boolean algebra, you can do all sorts of familiar kind of tricks. So one thing I wanted to point out is that this is, I mentioned last time, exercise. Every Boolean algebra has exponentials. Exponential given by b to the a being not a or b. And that's what gives rise to the truth table for implication that you learned back in school, is by saying the exponential in a Boolean algebra is given this way, and the truth table is just, when you do it with a truth table, that is the particular Boolean algebra with two propositions, gets us is derived by looking at that, by taking that as your definition of an exponential. Okay, so that's good. That was like a brief summary of where we got to last time, so you can do that. So I want those as exercises also. Okay, so we'll do this. So this will also be an exercise for you. This is not too difficult. Okay, so this is, that's good. And you can also check, and you'll probably need all these things. You can also do things like check various things like what is called De Morgan duality, which would tell us, for example, that you can prove this is the complement of A and B is the join of the complements, and dually the other way around. Okay, so you're sort of familiar with this. And you can derive these things from the properties I've given, so you can check those. You'll need those kind of things for proving that you have exponentials, I think. Okay, so that's where we got to. And now what I want to point out, and I want to, this will make a transition to part two, which is part two, and I'll make that transition here, is IPL from a sort of proof perspective. And this is where we start to understand where type theory comes from, at least if we look at it from the starting point of logic. There are many starting points. So this is what I'm going to do next, and we'll get there. But in order to make a transition, I'm going to make some remark. Sorry, what?
What does A star mean? Can you say it again?
What does what?
A star. Like when you
Oh, yeah, well, I wrote it on the piazza. I was summarizing in the piazza. You have to say, you're starting out with the logic, which I didn't repeat here, all these things. I had another judgment, A prop, okay? A is a proposition. And we define that by some rules. Then you can define, you're supposed to define what is a High-Ting algebra. Well, it's given by this data. okay, then you're supposed to say for every proposition, you can interpret that proposition into a Heyting algebra in the obvious way. So conjunction will turn out to be a meet, okay? Disjunction will be interpreted as a join. And if you do that, then you will find that the things that are provable are going to be true in this sense in every Heyting algebra, okay? And you just have to do that interpretation, yes?
Do you mean a complement negation right behind you at the Boolean algebra?
Yeah, this is a complement, right? Oh, this should have been complement, yeah, sorry about that. That's what yeah, sorry, I meant the right complement there, yeah, sorry.
One more question now. What is the relationship between exponentials and implication? Is it arbitrary, or is there actually an intuition that connects them?
Well, the exponential is defined, what do you mean? I'm saying that, for example, if you want to show that logic gives you an exponential, okay, well, what I was saying, what this remark is saying, when you're interpreting logic into a Heyting algebra, what you're going to do is you're going to take the exponential to be the implication. And it will turn out to be an exponential. What does it mean to be an exponential? It means it's the largest thing that when conjoined with A gives you B. Okay, that's the definition of an exponential. Okay.
Is that connected to exponentials in numbers?
Yes, because the origin of that notation or terminology will be a little bit clearer when I go over there. But the idea is you can identify, if you're familiar in set theory, the way this comes up, you can identify the power set of A with the functions from A to 2, okay, which is often written 2 to the A. And the reason is that the size of this thing, if you take the cardinality of this to be some kappa, then the size of the power set will be 2 to the kappa. So like that's one way of saying why that notation is used. But there's another important reason why the notation is used is because it's very important in the general case, just as it is important to distinguish between entailment and implication. It's important in the general case to distinguish between, I'll write a long arrow, mappings from A to B and the consolidation of such mappings as an object in the category, which is an exponential. Okay, and those are separable notions. So I mentioned that last time. For example, in the category of groups, you have group homomorphisms, those are maps. But for general groups, the collection of homomorphisms doesn't form a group. If you have an abelian group, you can give a group structure, or if you look at the group isomorphisms, you have a group structure, but in general you don't. So you can't necessarily internalize the maps as an object of the category in question. So it's important to keep those things separated, and we'll be talking about that sort of thing more a little bit later. Okay, all right. So now I lost my thread. Let me think about what I was in the middle of trying to say. Oh yes, okay, yes. So here's what I wanted to say, going back with the principle of logic. Okay, so I'm going to make a claim which has to get proved a little bit later. Okay, which is in IPL, and just intuitionistic proposition logic, not all instances of the law of the excluded middle are provable. Okay, so you cannot expect in general, okay, you cannot expect in general for generic A that for every A, you write it just like this. I'll just put this in paren here because I haven't defined exactly what that means. Okay, this to be true. Okay, and the intuition, and now what I'm going to do is develop that intuition a little bit more. But the intuition about this is supposed to be the following. Why do you not expect that to be the case? Because, so the idea of the proof is this. The idea why you should expect that not to be a case, it's not a proof, is via what is called the disjunction property. And that's what I'm actually going to discuss here now. And this will be a useful thing for me to use to motivate, which is the disjunction property, which says that, and I'm going to have to prove this, and we have to discuss how that could be proved, but I'll say, which says that if you can show A or B is true, then it can only be by virtue of the fact that you've shown A is true or B is true. So we'll come back to whether the disjunction property holds and what it means. But let's just say if we have the disjunction property, then what would happen is the law of the excluded middle holds. The corollary of that holding with the disjunction property would mean for every A, I have either a proof or a refutation. Either A true or A is false, which is refutable. So I have a proof or I have a refutation. And of course, manifestly, we understand that we do not have such a thing. Okay? So there are open problems in the world. Propositional logic is not very capable of expressing them, but I'm working my way up toward complicated things. So you just have to say, so if we took A and B to be an atomic proposition, like P equals NP, then we know perfectly well that no one has a proof or a refutation of that statement. So the idea is that because of this intuition about the disjunction property, okay, because of that intuition about the disjunction property, you would think that it should not be the case that the law of the excluded middle will always hold. Now I'm going to actually I'm actually going to prove this here. I'm going to show you the proof of this, okay? But before I do it, I want to motivate all of this a little bit more. So I thought I would only need one board, but I'm going to erase that column because I need more space, and we'll come back to that. That's where I'm heading, though. I'm going to end up there. Okay, so what do I want to say next? Okay, so what I really want to say is, in some form, I want to say there exists a Heyting algebra which is not a Boolean algebra, because you can easily check in a Boolean algebra that true is less than or equal to A or A complement. That's just the definition of what it means to be a complement. So if you're thinking of your negation as being complement, then it's trivial, okay, that true is below A or not, or A bar. But in a Heyting algebra, it is not, in general, we do not expect, in general, that we have either a proof or a refutation. This we do not expect in general. So there are different ways in which I can prove to you, okay, that would not hold in a Heyting algebra in general. And the main idea is to exploit the soundness property that says if something is provable, it's true in every Heyting algebra. That's what this is saying, left to right. So if I can exhibit a Heyting algebra in which it isn't true, this law of the excluded middle, then it can't be provable. Okay? So it's a counter model, right? So that's what we're going to do. And the counter model I'm going to construct is the model, or the particular Heyting algebra, that it derives from the rules of intuitionistic propositional logic that I gave you last time. So what we're going to do is we're going to look at and analyze the rules of proof. So what I'm going to do is a little bit of proof theory. I'm going to show you some basics of proof theory. That's what is going to happen. It's not to say that there aren't other ways, you know. There are other constructions one can do of things that are Heyting algebras that aren't Boolean algebras. That is completely true, but that's not the one I'm going to do. That's all. I'm going to do something based on proof theory. So it's not to say that there isn't any other way to prove this. Okay. So the thing I want to show straight away, which is very important, okay, is just because the law of the excluded middle isn't universally valid doesn't mean it never holds. And it doesn't mean that it's refuted. So let me mention this, okay? So, for example, what we will say, make a definition, we'll say a proposition, A prop, is decidable if and only if, just by definition, A or not A is true. So, when I say, sometimes this can get confusing, so if you don't mind me belaboring the obvious, okay? Just because it isn't universally valid, I will eventually show that, doesn't mean it can't hold in certain situations. So trivially, of course, we can take two trivial examples. Take A to be the trivially true proposition, and you can easily check that for that definition of A or not A is true, certainly, because truth is trivially true. And in fact, if I take A to be the trivially false proposition, then I will get A or not A is true. And so certainly there are decidable propositions. Okay? It's not to say there are no decidable propositions. Okay? So I want to contrast these two things. In a richer logic, like I'm just doing propositional logic, but where I could actually say interesting things, then one might imagine, this is a foreshadowing, that, for example, equality on the natural numbers you would expect to be decidable. Two numbers either are the same or they're not. I don't have, formally this doesn't make any sense right now, but you can see where I'm going. Oh, that should say not. Okay, so either m is equal to n or it's not. Okay, that's a very straightforward thing. And the intuition being these are finite objects. So by a double induction on m and n, I can just go through all the cases and give you a decision procedure by looking at m and n, and I can finitely inspect them. That's what the induction argument would be doing. And then by finitely inspecting the numbers, I will decide one way or the other. However, for real numbers, like if we were to have real, something like this, we do not expect this to be the case. This one we do not expect, this one we do expect. And I'm not proving it yet, but the intuition should be clear. I can't ever sort of finish deciding, okay, looking at x and y, like if you think of them as decimal expansions, and maybe this one is 1.0 and this one is 0.99999, and you keep working at that for a long while, well, you can never actually reach a decision. This is not a proof, but I'm just giving you a feeling. You can never actually reach a decision whether this is going to be always 9s, in which case it is 1, or not. That's a simple example. Now, the way you could actually prove this is by representing Turing machine execution sequences, for example, as decimal expansions. And you can say a machine halts if it veers away from 0 or not. And then you can actually, prove that there's no recursive decision procedure for this. But that's just to give you a flavor. So that's the notion of a decidable proposition. So we'll often be interested in decidable propositions. And we will also often be interested in the beginning to develop your intuition. I also need to define something like a prop is sometimes called stable if and only if not A implies A. I'll put in all the parens just to make sure it's clear, is true. And again, it's going to work out that not all propositions are stable. And I will get that out of proving a disjunction property and looking at the law of the excluded middle. So let me just write that down, and now I want to show you something important, which is the following fact, which will blow your mind, I think, I hope. That's my idea. So the thing I was trying to say here is by the fact that there are decidable propositions, then it's we certainly don't have the negation of this. But in fact, we can really show something stronger, and this often confuses people. We can show for any A that it is not the case that the law of excluded middle is refuted. Okay, so it's kind of, so this is the thing I wanted to show you a proof of this. And then this is related to stability, because if all propositions were stable, then the proof I'm about to show you would allow me then, by stability, to drop that double negation, and then I would get the law of the excluded middle. So ultimately, I'm going to refute stability by refuting the law of the excluded middle in the sense that I'm sketching over there, and we'll pick up in a moment. Okay, so, but you can prove this outright. And this kind of thing people find confusing when they first encounter like constructive logic because they're used to canceling negations like without thought, okay? And they find it very troublesome to see these double negations. But I would like to get you into a position to feel that that's not troublesome at all. And the idea is it's a perfectly ordinary thing in everyday life. If I say to you, I don't dislike chocolate ice cream, it's not the same thing as saying that I do like it, okay? It's a weaker statement. And in fact, I will often say that, well, I didn't really dislike that course. but it's clear that I didn't really like it, okay? So it's a weaker statement. So the idea is that there's a weakening is being done with the double negation. That's the first kind of observation I want to make. But the other way to read it in order to keep your wits about you is to say, all we're saying is, put a paren in here, it's not refuted. This would be that the law of the excluded middle is refuted. And by the remarks I've made so far, we should hope it to be the case that it is not refuted, because then we'd be inconsistent, because even truth gives us an example of an instance of the law of the excluded middle. So we can say, so this says that the law of the excluded middle is not refuted. So I'm using this as an example to get you used to a mindset that is going to be very important to us, okay, throughout the whole semester, and that's what I think is interesting. So how do we prove this? Okay, so there's an easy proof, and I'll just write it down. But I'll bet if you haven't seen it before, you will not find it hard to understand. You'll be able to follow it locally, but you won't. You'll be like, oh, you'll see. Okay, so what could I possibly do? It's a little bit crazy. Okay, so I want to prove a negation, and this brings up a point. I don't know if any of you had time to watch Andre Bauer's lecture on the what did he call it? The 5 stages of accepting constructive mathematics, I think is what it was called. Okay, and if you watch that, you'll see that some of this plays out. One of the points that he made there, which is quite true, is there's a common misunderstanding about constructive mathematics that somehow or other you can never mention the word contradiction. Okay, well, this is like complete rubbish, okay? This is totally false, okay? That's just like, I don't know how that happened, but somehow people got this feeling. And I wish to distinguish what is going on here is I wish to distinguish, okay, what is actually a proof by contradiction from a proof that happens to use a contradiction. So the point is that if you ever want to prove a negation of something, that something is not the case, basically what you do is you assume it is the case and you derive a contradiction. That's a perfectly valid thing. What is not valid is if you want to show that something is positively the case, to assume that it isn't and derive a contradiction from that and then say that it is. Because that is making use of the law of the double negation, which I'm going to show isn't true. So if you want to show A by assuming not A and deriving a contradiction, then what you really get is not A, because you've refuted the negation, but you have no license to go from there to A. That's an actual proof by contradiction. So there's a big misunderstanding, and this is like one of the reasons why people why there are 5 phases of accepting constructive mathematics, and that's part of it. Okay, so we're going to prove a negation. So how are we going to do this? So we suppose, for the sake of the contradiction, that this fails. This is a generic A that I'm doing here. Suppose that this fails, and now, just to be very explicit, I want to show falsehood or a contradiction. I'll often write it like that. So I want to show a contradiction. If I can do that, then you'll agree that I have shown that it's not refuted. Okay, so now it's like this is one of these kind of follow your nose proofs, because at each moment there's pretty much only one thing you can do. And so you figure out, okay, so what in the hell am I going to do? The only thing I've got in my hand is this negation. So the only hope I have for using this assumption is it suffices to show A or not A. Right? Because if I show A or not A, then because of this assumption, I get my contradiction. But of course, you immediately think I'm chasing my tail, okay, somehow, and I can't possibly do this. Okay, but watch me do it and then see what's happening. So I'm actually going to prove A or not A, okay, at this moment. You think, how the hell am I going to do that? Well, if you look at the rules that I gave for intuitionistic propositional logic, I have 2 sort of basic ways I could prove A or not A. One thing I could do is prove A, but I know nothing about A. A is completely generic. And I don't have any assumptions hanging around that govern A, so it doesn't seem very plausible that I'm going to be able to go in that direction. So I just boldly carry on. I don't know what I'm doing, but let's just say the only shot I have is to refute A. So it suffices to show that A fails. Because if A fails, then A or not A, and if I have A or not A and I have that assumption, then I have a contradiction. Okay, and how am I going to do that? Well, the only way to show a negation is you suppose A, and what do you show is a falsehood, right? Contradiction. So that's what I need to do, right? But if I know A, then I know A or not A, of course, because if A holds, then A or not A holds. Oh, but then that contradicts the assumption here, which is a contradiction. And I'm done. It seems. Okay, so that's what I've done. Oh, let me double check. Yes. All right, you probably do not feel comfortable with that. Okay, so what is going on here? Somehow I've just spent, who knows how long trying to tell you you don't get law of the excluded middle in general, and then I just seem to show it in general. But I didn't show it in general. I showed it in general under the assumption that it fails. That's a weaker thing, because I have additional assumption hanging around. And in the presence of that assumption, I can show the law of the excluded middle, which is my contradiction. And I do that by showing the right disjunct, which I do by contradicting that assumption. So there it is. Okay? So it's a fallacy to think. So it's very elementary. I'm not saying that. But I still think it's a little like, ooh, it's a little crazy thing, okay, that comes out here, and you kind of have to get used to that. Okay, so this shows us as a corollary, if you believe me, which I'm going to have to argue for you, that you cannot get the law of the excluded middle in general, then the corollary, of course, is not every proposition is stable. Not every proposition is stable. Okay, so that kind of reasoning, that kind of thing will come up a lot very shortly as well. Okay. All right, now I want to show you something very useful, and we'll develop a lot of intuition for type theory that we will exploit later on. Okay, so I have to make some space for myself. Okay, so now what do we want to do? So I want to go back to this claim. I want to go back to this claim about the law of the excluded middle, and I want to go back to this claim about the disjunction property. So I want to claim that IPL has what is called the disjunction property as written here. So the question is, how would we prove the disjunction property? I'll just write a DP for IPL, intuitionistic propositional logic. Well, there are probably a lot of strategies, but I'm going to show you an obvious strategy. So let's write out very carefully, because I need to remind you of something. Oh yes, let me. There's a little dependency ordering. Okay, yeah. Oh, okay. All right. So how do we do this? So here's what I want to do. I want to remind you of something about the inference rule. So when I wrote down the inference rules, remember, this is just a reminder off to the side here. We're going to need this in a minute. When I wrote a rule like this, A true, let me leave a little space. I did make this remark before, but I think it's worth me re-remarking it, which I called the conjunction introduction rule. I said what this stands for is all possible instances of it under assumptions. That implicitly, we write here, it's really for all gamma. Okay, that is written like that. That's really what's going on when I write that rule. I write it down in a short form because it's kind of nicer to omit carrying along all that clutter, but the meaning of it is it holds for all gamma. Okay, that's the idea. And we do this for all of the rules we had so far. So in other words, the rules of the logic now, so what we do is we interpret the rules that I gave you of IPL as an inductive definition of a consequence relation of entailment. This is the key step, okay? So all of the rules of logic define for me this judgment A true for a variety of gammas and A's. Okay? And if you think of it as an inductive definition, what it means is, and let me make a little space for myself here, what that means is that we have a notion of sort of derivation trees, which are usually right D, which ends here, and these are finite depth things. This is a finitary inductive definition. It's also finite width, but one could consider infinitary derivations that are infinitely wide but finitely deep. Okay, that does happen, but not here. Okay, so A is, so we can have a derivation that A is true. So that's what I mean by it being an inductive definition. That is, for this to hold means you can piece together by composing all of the rules that I gave you and wind up with that as a conclusion. So now what we're going to do is, so what our theorem is going to be, and this is important, if under no assumptions, I will stress it here. I'll write it like this in order to stress. If under no assumptions you prove A or B is true, then under no assumptions you either have A is true or under no assumptions you have that B is true. That's the disjunction property, okay? Written out, okay, carefully. Well, why do I insist on no assumptions? Well, because it's perfectly obvious that if I assume some disjunction, then of course that assumption is if I assume this disjunction, oh, I'm getting ahead of myself. If I write it like this, if I assume, excuse me for getting ahead of myself, okay, if I assume the disjunction and derive it just because I assumed it, well, there is nowhere in sight that if that's my entire derivation right there on the board, there's nowhere in sight are you going to find a derivation of A or a derivation of B because I just assumed the disjunction. So you don't get it for general gamma, okay? That's like one could possibly characterize the class of gammas for which one can get this, but never mind that. Let's say empty. Okay, that's what I'm going to be interested in, okay? Because that'll be enough to get me what I need for the law of the excluded middle. So this is the idea of the disjunction property. And how do we prove this, okay? Well, the proof would be something like an induction on derivations. And I want you to see basically how this breaks down. So you do some induction on derivation. That is, you examine all possible derivations D that end with A or B is true. You just go through what are the derivations you could possibly have there, ending with A or B is true, and then you hope to say that no matter what happens here, somewhere buried in here must be a derivation that A is true or B is true, or even if it's not buried in there, there's enough data in here somewhere that I can piece it together and get a derivation that A is true or a derivation that B is true under no assumptions. Okay, so that's the strategy. It's an obvious strategy, and it's not really going to work, okay, which is what I will show you next. Okay, so depending on how you happen to approach the problem, you might start out getting sort of lucky, and you might be optimistic. So you say, oh, let's look at all the possible derivations. So here's one thing that could happen. What could this derivation look like? Well, the last step of the rule might be or introduction sub 1, in which case what I have here is a true for some reason, I don't know, all right? And you just say, there it is. That's the one I'm looking for, and I'm golden. And in fact, you look at this, or I2, and you say, oh, well, the premise of that rule is literally exactly B is true, and that must have some derivation, and I'm golden. This is the guy I want. Okay, I extract that. So you start to feel a little bit optimistic, okay? Because you think, oh yeah, I see, I get it. This makes some sense. By the way, there's something I forgot to mention to you. When I wrote down the rules for intuitions through proposition logic, I know that I presaged them by calling them intuitionistic propositional logic, but I kind of want to point out to you, nobody objected to those rules. They all seem good to you. Okay? And I dare say, if I had asked you just to write them down, you'd never seen them before, you'd probably write those rules down. And yet, as I'm in the middle of showing, they don't validate what you consider to be standard reasoning principles. In particular, they don't validate the law of the excluded middle. So the thing that's weird is, I pulled one over on you, but where did I do that? Because everything seemed perfectly plausible. Okay? The rules all seemed like the right thing. I'm putting words in your mouth or thoughts in your head a little bit, but nobody objected, okay? And yet they have, I'm in the middle of showing, they have this unexpected consequence. Now, why might that be? Well, there are different ways to think about this, okay? I'll tell you the one I favor. Basically, everyone really is a constructivist. And they've been trained to believe in this other thing that we're discussing now. So I'll show you why. I'll try to substantiate that a little bit later. Okay, that should annoy you enough to make you pay attention to everything I'm going to say so far, which is my goal. Okay, so we're back to doing this, analyzing all the derivations. And we start out, we look at those two rules, which are the only ways in which you could introduce an or. And by the way, the rule of assumption doesn't apply because I'm considering only closed derivations, ones with no assumption. So it's inapplicable. So the example I inconveniently erased of A or B true following from the assumption, or even some composition of assumptions, that's irrelevant because there are no assumptions. So the assumption rule is inapplicable, and you start to feel optimistic, okay? Because then you look around and you say, well, let's look at conjunction introduction. Oh, well, the bottom of a conjunction introduction rule is a conjunction. And a conjunction is not a disjunction, so that rule doesn't work either. So conjunction introduction is inapplicable. So we don't have to worry about that. And the same holds for implication introduction and truth introduction and false. There is no false introduction. Truth introduction and are all inapplicable. So that's nice. We're making progress. Things are looking pretty good. Okay. The disjunction introductions, they cover the case. So now I have to go through and worry about, the elimination rules. So now you probably have anticipated this. Well, suppose my derivation looks like this. I get A or B is true. I'll keep writing from no assumptions just to be emphatic. But suppose the way in which I got it was by showing that from no assumptions, some C implies A or B. And separately, you showed C. Let me make some room for myself. So I have a derivation here, D1, and I have a derivation here, D2. Okay? It's like that. Now, of course, you're starting to sweat. Because this isn't, now we're in trouble. Why are we in trouble? Because C is completely arbitrary. You have no control over what C there could possibly be, okay, that was sufficient for a disjunction that I can prove, okay? You don't know. And the theorem, like if I try to apply induction somehow, the theorem is not going to give me, at least as stated at the moment, it's not going to give me any ability to understand like how to deal with this case. And a similar thing would happen with conjunction elimination or even disjunction elimination. But this is enough to illustrate the case. So here we get into trouble. So for all you know, there's this kind of indirect proof that says go via a lemma the mysterious, weird lemma that for all you know exists, which implies A or B, and then I conclude that from A or B. And the question is, how do you rule out that such a lemma could possibly exist? Okay? That's not so easy now, because you're now starting to think about, in intuitionistic propositional logic, you might be emboldened to think you can do this because it's so simple, but I want to I'm going to put this in a larger setting eventually. So you don't have any control over this guy, and it's not going to be so easy for you to figure out that no lemma could possibly mediate the deduction of this fact. Okay, it's going to be hard to do. But here's how you would go about doing it if you were to do it. You think about it for a moment and you say, oh, I have an idea. The idea is this. If you have this premise like this, so this is my D1. What you would do is you would like to argue, okay, that, well, wait a minute, how could you possibly have proved C implies A or B? Well, you would like to argue, you would like to say, oh, well, wait a minute, this must look like this. You would be wrong, but you would be right-ish. You would say, it must be the case that I can deduce A or B from C somehow. So let's call that D1 prime. Okay, it must be the case, you would say. And then you know over here you've got D2, which gives me that C is true. And then you say, the way I'm going to deal with this is I'm going to inline the lemma. What I'm going to do is I'm going to say this whole thing can be plugged in for this assumption. So this assumption appears here at the leaves. Over here at the leaves, I'm using the assumption around here. And so to redraw this picture, what I want to do is I want to plug in all the D2s that you get here so that I get a derivation of A or B true without any C. And then I apply an inductive hypothesis that says this smaller derivation gives me A or B true, and therefore I get my, so I still have my, sorry, I got as far, yeah, so I was right. I would get A or B true, and then I would extract from that by induction the proofs of A true or B true from that.
In what sense is it smaller?
Okay, what's that?
In what sense is it a smaller derivation?
Is something?
In what sense is it
Yeah, well, there's a lot to be said. Okay, but I'm giving you an idea, okay? In what sense is this derivation smaller? Because it looks a lot bigger, doesn't it? Okay, so that's an interesting problem that I will come back to later. It looks bigger because I've taken this derivation, which is whatever size it is, and replicated it. In this case, I depicted it 3 times. So it certainly looks like this whole thing is much bigger than that whole thing. If by bigger you mean count the number of nodes in the tree. But there are other measures you can assign. So I'm going to think about, I'll hold that in abeyance. I'm trying to give you an intuition right now, okay? I'm not actually doing a proof. But yes, eventually one has to face the idea of a measure. But this would be kind of your idea. And notice that what it relies on, it relies on transitivity of entailment, amongst other things. Okay, which I talked about before. Because it relies on the idea that if I can show that C true entails A or B true, and C is true, then by clicking these things together, this is one of the structural properties, then A or B is true. That's what I used here. So I relied on transitivity, which was one of the structural properties of entailment. I also relied on something else, which is, well, I relied on several something else's. One is what Arbob mentioned about the size of the derivation. And the other thing I relied on was that this implication must inevitably look like this. Well, that's not obvious either, because I could derive an implication from another lemma, D, and D implies C implies A or B, and then you've got D. Okay, so it's not obvious that this is the premise of that rule, okay? But you kind of feel that some way, eventually, you must get a deduction of this from this. Okay? This is true of constructive logic. It's not so true of classical logic, actually. So all these intuitions that I hope to get you to feel, you will feel them, I hope. That's my plan. And all of that is by way of pulling you up to the stage of acceptance of constructive logic. That's my goal, okay? Because I think that I personally think you have a lot of intuitions that actually don't apply to the logic you use. So that's but you don't need to accept that. You can just ignore that as rubbish, okay, for various reasons. But I have a little kind of meta goal in mind to show you that. Okay, so I relied on some dubious thing that I must go from here that I'm going to come back to. But I certainly relied on this idea of transitivity, because even if that dubious thing held, the next step was to apply transitivity in order to get rid of this assumption C, so that inductively, let's hope something smaller, so that inductively I can extract from here a proof of A or B, a proof of A or a proof of B, and then I'd be good. All right? So that was the plan. So let's now look at the structural properties. What makes us think that the structural properties hold? Because I mentioned them, but now but what I really need to do is I have to prove them. I have to actually show you. And I'm going to sketch it at first, and then I'll set up a framework which makes it very easy to prove in a nice, clean way. But let's just do the sketch. So let's revisit the structural properties. I won't write them all out because we wrote them down before. Let me just focus on one, just for the heck of it, which is weakening. Remember what weakening said. So what I'm going to say is the structural properties are admissible. This is what I'm going to do. This is some terminology that you should know. Okay, things are admissible. What I mean is like the following. Like weakening is admissible. What I say is if you can derive A true using the rules of IPL, let me just like write it there to emphasize the ones I gave you, then let me call it B. Then I can also derive, in the presence of an additional assumption, IPL, that B is true, with A being around, where A is a proposition. So it's stated like this. Okay? So that's called an admissibility. And sometimes the way people will write it is they'll say, the following rule is admissible. Okay? And they'll write it like a rule that says, if A is true, B is true, then gamma with A true gives me B is true. That's the same, just another way of saying the same thing. The following rule is admissible. The point is, don't think of this as a primitive rule defining the system, saying, here's a rule of interest. It's admissible in the sense that if you give me a derivation of this, then I can turn it into a derivation of that. Okay, that's what this is saying. So it's a nice constructive proof. So why is weakening admissible, just to develop your intuition? Well, weakening is admissible. What is the proof of this? Okay, so why? Why is weakening admissible? Well, let me write it in a short way. Because the rules are polymorphic. Because remember, when I had a rule, let's go back, A true, B true, just give me an example, and B true. I said what that really means is it's polymorphic in gamma. If you have this, you have this, you have that. That's what I really mean. Okay? The rules are polymorphic. So if I derived my conclusion, if the B in question, all right, so let me redo the lettering to make it look nicer. So let's call that B1 and B2, because that's my B. All right? 1 and B true. So that's my B in order to make everything match up nicely. So what I get to do is, inductively, I get to weaken this to gamma A true gives me B1 true, right? Inductively, I get to weaken this to A true with B2 true, right? And then, because the rule is polymorphic, just take the gamma to be this bigger gamma, and then I will get, by applying this rule, to be gamma A true gives me B true. You see what I mean? It's because the rule is polymorphic. The rule holds for any choice of gamma. So if I inductively weaken the premises, then I can reapply the rule. But when I reapply the rule, it used to be applied to gamma. I will now apply it to gamma with A true because it holds polymorphically. So when I instantiate it, I will get the conclusion in this way. And then you just say, etc. In other words, all of the other rules go the same way, okay? Except there's an issue of the order in which you do the lemma, so you have to be very careful. The way I wrote this is the weaken assumption has to be last, because this is a sequence. So really what you want to do is prove, what you really want to prove is for general A, just call it gamma prime as a general gamma prime. And then you can redo this argument in the same way. Put some general gamma prime here, and you put gamma prime here, and it will continue to work. And the reason you need to do that is because of implication introduction. So if you check the rule, you will see how that works. So you're going to have to look at that. And similarly, you can do exchange, which says the order of hypotheses doesn't matter. And you can do contraction, which says that duplicating a hypothesis is the same as just writing it down once, so that you can be able to do exchange and contraction. What about reflexivity? This must be taken as primitive. You must have a primitive rule that if I have a gamma with one version of it is A true, then A true. That must be taken as a primitive rule. You can't get that without that rule being around. Okay? So that one you build in. And what about transitivity? And this I will leave as a homework. This is a homework. Prove transitivity. And I would say, for the sake of your sanity, just do it for IPL minus, okay? The negative fragment, because that's enough to give you the main points, yes?
I thought you have to prove exchange before we.
Yes, I said there's an issue of the staging. So you have to prove exchange first, yes. I just happened to pick weakening as the one I'm illustrating. Okay, so part of your note-taking and homework is what you want to do is you want to think through everything. How do you prove these structural properties in order? It's very enlightening to do it, so you can think about it. And if you do transitivity, you should be able to do this, okay, for the negative fragment without a great deal of difficulty. But now I'm going to introduce something that will make that easier to do and easier to write down in a second here. So let me check where I am. Okay.
If you want to prove
Okay.
exchange admissible,
Yeah.
can you use the reflexivity rule in that form, or do you need to be like gamma, comma, A true, comma, gamma prime?
If I want exchange to be admissible, can I? No, if weakening is admissible, I can just omit that and state reflexivity this way, because if I have weakening, but if I don't state reflexivity this way, I won't be able to get weakening for reflexivity, because the reflexivity rule won't allow me to put in some new hypotheses. So,
Right, but
yeah.
you wanna
So you got to be careful about all those things.
You
Yeah.
want to get exchange before you even get.
Yeah, it's nice to get exchange first.
Right. And
Okay.
so wouldn't it be hard to get exchange if not?
Oh, I see, yes. So then to make exchange work, so you're probably right. I should probably write it like that. Then once I have exchange, then I can think of it as last. Yes, you're right. So there's a little delicate thing here about getting the order right. I don't want to spend a lot of time on this, okay? But what Arbov says is completely correct, but okay. All right, but now, okay, so now that's the first point. So going back to my putative argument for the disjunction property, one thing I found myself wanting is transitivity. That is, I wanted the structural properties of entailment to hold. So what I did now is just sketch for you how it would be, okay, that you prove the structural properties of entailment. Okay, so that's done. So we now have defined a good logic. Okay, so one thing to point out is there are criterion being put forth here that tell us that a logic is not just some arbitrary set of rules that you wrote down this week with whatever nonsense you want above or below the line according to what looks good to you. okay? That's like not what a logic is, okay? So there are some criteria for saying when you have won, when you have done it properly. So a first criterion is that the structural properties should hold, okay? If you're in a situation where the structural properties don't hold, then you've done something wrong. You're not talking about logic anymore. Okay, substructural logics will allow us to play with contraction and weakening exchange, I mentioned that, but certainly reflexivity and transitivity a damn well better hold. Otherwise you don't have any notion of entailment at all, and then you don't have a logic. Okay, so that's important, and you'd be surprised how often people don't appreciate this point. So that's why I bother to mention it. Okay, all right, so now the next thing. So the next thing is Genson's great idea, okay, which is Genson's insight, which goes back to what I was saying before. So what is Genson's great idea? So Genson's great idea can be, let us now reconsider the situation I was sketching for you before. I was trying to prove the disjunction property, and the reason I was doing that was I wanted to exhibit a Heyting algebra that is not a Boolean algebra. So I wanted to show you in particular that the law of the excluded middle would not hold generically. Okay? That is the idea. So I'm doing that by analyzing all the proofs. That's the strategy I chose. Okay? So that's what I want to do. Okay, so we started looking at a proof, we started looking at an argument of how this would work. And we ran into this very interesting case. Okay? All right, which looked like that, and we started to think about how you might handle it. Okay, and that's how we got us to thinking about the structural properties. But there's something very interesting about this case. And if you look at how we handled it, here's what we did. What we did is we said that what's going on here is, in the case that we considered, if you don't mind me erasing in place here a little bit, what we did is we said, well, we think it's sufficient to consider the case in which we have this is the case by implication introduction. This is implication elimination, that's implication introduction. And if I do have that situation, calling that D1 prime, that's what I had over here, okay, what we said was, the idea of the argument was that the elimination rule should cancel the introduction rule. I have a very peculiar situation where I did an introduction of an implication only to immediately discharge it. And then you say to yourself, well, that's like some kind of bizarre thing to do, because why did you go through all the trouble of proving an implication only to then immediately prove the antecedent and then get rid of the implication? After all, what you can do is just get rid of the digression, okay, and just focus on plug this into here. Then I get a closed derivation of A or B all by itself. I don't have the indirection, and then I can recover by induction that, in a sense, to be made precise momentarily. I can recover by induction a disjunction property from here and then transfer it to here, and I'm done. So Genson's key insight is the inversion principle. And this is why is it so interesting? The reason is that this is the origin of computation. Okay, so the inversion principle says informally that elim is post-inverse, at the very least, is post-inverse to intro. I'll write it like that. That is, if you ever have a situation, let's do another blatant one, where I have A true, B true, A and B true by an introduction, two derivations, D, call it dA and dB, why not? Okay, and then I immediately follow that by and elimination 1 maybe, and I make A true. Well, I can simplify this, I can cancel that, and just turn that into dA, which is a proof of A true, and why bother with all that other rubbish? Because you just wanted to, all you cared about was A after all. So what you do is you say that the elimination rule, so what we're kind of saying here is and elim left composed with and introduction, okay, of like something like D1 and D2, So like that should be equal to, in some sense, D1. And now I'm going to make that idea precise. But this is the informal idea. And the reason this is interesting is because this gives rise, well, it's interesting as a meta-theoretic technical device because this is how we will put meat on these bones, okay? What we're going to do is we're going to prove what is called the normalization property, which says that if you cancel all the pairs of intros and elims fully, you will end up with what is called a direct or normal form proof. And in a direct proof, this kind of digression cannot occur. And now if you look at all the direct proofs of a disjunction, the only ones there are, it must end with or introduction or 1 or 2. And in that case, I have the required derivation implicit in the proof. So that is the idea. So what it does is it gives rise to a dynamics of proof. So this is the fun thing, a dynamics of proof. You see, I'm making a transition now. Traditional treatments of logic, Roman numeral 1 in the beginning of this lecture, only look at provability. They don't look at the proofs themselves as objects of study. And in particular, you can't run them. And so, you know, you may or may not agree with me on this, but, you know, a lot of times students enjoy programming much more than they enjoy math because you can run the program when you finish it, okay? And with the proof, you just like do the proof. Okay, that can be a very satisfying thing. I'm not trying to say anything like that. But you can't do anything with it. It doesn't do anything. But if you have a proper treatment of logic in the style I'm doing, we're actually going to have a dynamics of proof, and you're going to be able to run those proofs. And in fact, what we're going to end up being able to do is we'll have a complete identification of programs and proofs. And then the result of that, and that's what I'm going to be doing throughout the semester, is that you have no difference between math and programming. That's the beautiful vision that we're trying to develop. And this is, okay. And moreover, we will know, because of connections has yet to be developed with category theory, by looking at the connections between proof theory and category theory and programming languages or type theory, then we know what we're doing is canonical. And then all sorts of subjective disputes just like evaporate, okay? Because you have like real facts on the table. So that's the whole sort of goal, is to try to do that. Okay, so we get this idea of a dynamics of proofs. So now the intuition will be, by applying Genson's principle, I will be able to, I'm going to show you how to do this, and it's not, that's going to take a whole lecture in itself. I'm going to be able to get rid of these digressions, and once I get rid of the digressions, then the only derivations that I can possibly have will be by or introduction, left or right, 1 or 2, and then I will get the disjunction property. Okay, that's the idea. Okay, so in order to do that, what I'm doing is I've now like broached the idea that proofs are mathematical objects that are worthy of study. That's my action. That's what I really wanted to do in order, by bringing all this up. Which brings me to proof relevant logic. Which is really type theory. Okay, so that's what I'm going to do. So what we've done now so far is we looked at the traditional proof irrelevant, provability formulation of logic, and we got ourselves into a position where I wanted to distinguish this idea about double negation elimination, or distinguish between between a proposition as double negation, and to discuss the role of the law of the excluded middle, which will be very central to the homotopy type theory. Because, oh yeah, let me mention one other thing. If you took a Heiting algebra and just added in the axiom that for every A or not A, you have a Boolean algebra. Okay, you'll have to check that. Okay. So that's part of the relationship between the two of them. But in the general setting, which I'm now beginning to develop, if we were to do that kind of thing globally in type theory, we would completely ruin the subject. Okay? So that's a very key idea. So the whole idea of the homotopy theoretic interpretation of type theory depends on constructivity. That's why I'm spending this time talking about constructivity. If you don't have an appreciation for constructive logic, at least what it is, whether you like it or not, is secondary consideration, then you won't be able to understand what's going on with homotopy type theory. Putting it the other way around, once I get through with you and show you, for example, the beauty of homotopy type theory, you will then reconsider how you think about constructive logic, I think. So that's my double game here for the semester. Okay, so what is proof-relevant logic? What I want to do is I want to change this idea of an entailment, AN true, which is just logical entailment, A true. I want to generalize this to the following idea. I want to record a syntax for proofs. All these triangles and stuff I'm doing here get pretty awkward and clumsy. So I'm going to have a nice syntax, a grammar of proof. So this is going to be a proof object or a proof term or a piece of evidence, or there are lots of words that are used here. Okay, it's a constructive witness for the truth of A. You can say witness, you can say realizer. Okay, there are many terms that people, a bunch of terminology people use. It's called a proof term, which says this is a proof of A. I'm going to write down a syntax for it because, you see, I've gotten you to the point where we want to analyze the structure of proofs, and so now let's just write down what they are so that it makes it easier to do that. And corresponding to the assumption is the concept of a variable. So these are our variables, which are unknowns, of course, that's what variables always are, okay, which are unknowns, or they're lemmas, or they're assumptions, or they're axioms. I don't know, call them what you want. There are a lot of different words that you can do here. But the thing I want to get across is that they are variables. And in the sense of, ordinary mathematics. So in particular, to finish for today, let's revisit what the rule of transitivity says, okay, in this notation. If I have a proof of B from an assumption A, call that assumption X, and I have a proof of A, then I can combine those using an operation called substitution. B, and this is substitution. And then we also have the reflexivity principle. The variable rule, this is reflexivity, this is transitivity, or the variable rule. If you have a variable, you can use it. If you've introduced a variable, you can use it. That's what this says. If you have a variable and you can provide a proof term for it, a lemma, if you will, then I can inline the lemma and I can do substitution. So when I asked you to prove the transitivity is admissible for the negative fragment of intuitionistic propositional logic, what I really did is I said, write out what are the proof terms, and I'll do that next time I ran out of time. What are the proof terms for that fragment? And then write out what is the definition of substitution and do it. Okay? So show that this rule is admissible. That is, if you do this for a suitable definition of substitution, then you do that. So it's just plugging in. So the thing that this establishes in the beginning, that's the first thing. And then the second thing is we're going to connect this up with the idea of a mapping, because we will also be able to think of this as M is a mapping from the product of A1 through AN to A, in which will have the structure of a category. And in fact, it will be a particular class of categories. The generalization of the Heyting algebra will be what are called the Cartesian, in fact, Heyting algebra would be bi-Cartesian closed categories. Bi-Cartesian closed categories. So I put the parens there. A closed category is one that has an exponential object. It has an internal hum, as it's called. Bicartesian means that the exponential is right adjoint to product. We'll explain that. And we also have coproducts that'll be in there. So we'll explain that. So this will be the analog or the generalization of the notion of a Heyting algebra. Okay? So that's where we'll connect it with categories. So the idea is that proof terms are mappings in a category. Those are the same thing. This is a logic-looking way of writing it, or a type-theoretic way of writing it. This is a category-theoretic way of writing it. Okay? It's almost a notational difference. The main difference is in the treatment of variables, which is a little clumsy over here. Okay, but this is a very convenient treatment of variables. This is a very inconvenient treatment of variables. So we'll get back to that a little next time. Okay, so proof-relevant logic will give us rise to type theory and category theory. That's what we're doing. And so that's so that's where I'll stop today. And next time I will pick up how you prove Gensen's normalization property. And there are lots of ways to do it, but I'll show you a particularly useful way. And I have a reason for wanting to do that. Later on, I'm going to want to use similar ideas to give a computational interpretation to richer notions of type theory. So I'm trying to give you the tools that we're going to need to build them up. So, okay, we'll keep going from there. Thanks.